Turbo lag is one of the most misunderstood concepts in automotive engineering. It's often described as a flaw or something that engineers simply haven't figured out how to fix. But in reality, turbo lag exists because of fundamental physical constraints, not poor design. To understand turbo lag, it helps to think about how a turbocharger actually gets its energy. A turbo is not powered directly by the engine. It is powered by exhaust gases leaving the engine. That means boost pressure can only be generated after exhaust flow increases. When you press the throttle, fuel and air increase almost instantly, but exhaust energy does not. The exhaust gases must first build enough pressure and velocity to spin the turbine wheel. Only then can the compressor begin forcing more air into the engine. That delay between throttle input and boost response is what we call turbo lag. One major contributor to turbo lag is rotational inertia. The turbine and compressor wheels are relatively small, but they still have mass. Spinning them from rest to over 100,000 revolutions per minute takes energy and time. Larger turbochargers have more inertia, which means they take longer to accelerate, but they can move more air at higher engine speeds. This leads directly to one of the core engineering trade-offs in turbo design. Small turbos respond quickly but limit top-end power. Large turbos produce more power but respond more slowly. There is no design that eliminates this trade-off entirely. Another factor is exhaust gas energy itself. At low engine speeds, there simply isn't much exhaust flow available. Even with perfect design, a turbocharger cannot generate boost without sufficient exhaust energy. Engineers can reduce lag, but they cannot create energy that doesn't exist. Modern turbo systems attempt to minimize lag using several strategies. Twin-scroll turbochargers separate exhaust pulses to improve turbine efficiency. Variable geometry turbos adjust internal vane angles to increase exhaust velocity at low speeds. Some systems even use electric motors to assist turbo spool. All of these technologies reduce turbo lag, but none eliminate it completely. They work by improving how efficiently available energy is used, not by bypassing physics. There's also a misconception that turbo lag is always bad. In many cases, a small amount of lag is intentionally accepted to improve efficiency, reliability, or peak power. Engineers often design systems around predictable lag characteristics rather than attempting to remove lag entirely. This is why turbo lag still exists today, even with decades of advancement. It is not a failure of engineering. It is the result of balancing competing requirements: response, power, efficiency, durability, and cost. Turbo lag is not something engineers ignore. It is something they manage, shape, and work around. And as long as turbochargers rely on exhaust energy, some amount of lag will always be part of the system.